in like the whiteboard feature, you can type text. Wait 1 second. Give me 1 second. 你这个 copy 不了啊。
哪个？
这个题。
copy 不了。
Okay. Are you fine? Like just without the question? Do you have the question on paper?
Yeah, I have the question.
Okay. Oh yeah, and you can also like type it out. I think there's a text box feature, so
yeah.
I guess that's easier.
Okay. Let me find the question. Okay, so how I approached this problem was to take everything mod 99 because we want.
Wait 1 second. 我们应该先给大家讲一下这个问题是什么，万一大家这个没看，然后也没。Oh, okay. All right, continue. Sorry for the interruption.
Okay, so, and you want the smallest multiple of 99. So when an is equal to 0 mod 99, and so when you take it mod 99, it becomes an is equal to n minus 1. Oops, n minus 1 plus n. And so now we have an easier recurrence to work with. So I listed the first few values because that made it easier for me to see what it is. But this step could be skipped. I think it's 33 and 46. Then I noticed that for any term n greater than 10, it could be represented as n times n plus 1 divided by 2 minus the first 9 terms, which was 9 times 10 divided by 2. So subtraction. And we wanted this to be 0 mod 99. Okay, and then so basically you combine the fractions and the numerator has to be divisible by 99 since 2 is relatively prime to 99. So you get n squared plus n minus 90 is congruent to 0, or like n plus 10. This factor is n plus 10 and minus 9. And then, so I just started looking for factors now. Maybe this one was 11, divisible by 11, and this one was divisible by 9. Or the other way around. And then once I did that, sort of guess and checking, I got the smallest n was, what did I get? The smallest n was 45. So that was my answer.
Okay, great. I don't think I have much to add on to that solution. And does anybody have any questions? No questions?
Do anyone has a better solution?
No? Okay. All right. So let's just move on to the next question. Question number 2. And sorry if I look like I'm looking towards the ceiling because I'm looking at my other monitor. Okay, so question 2. Does anybody want to explain question 2? Because it's still like, yeah.
I could explain it then, if no one else wants to.
Okay. Okay, so yeah, sure. You may go ahead and explain.
Okay. So I just said that if 5 is the median, then if we like, oh, let's show the board first. And like if 5 is the median, or what is it? M equals 5. Oh, should I read the question aloud first?
Sure.
Okay, so like consider arrangements of the 9 numbers 1 through 9 in a 3 by 3 array. For each such arrangement, let A1, A2, A3 be the medians of the number in rows 1, 2, 3 respectively. These are the rows. And let M be the medium of A1, A2, A3. Let Q be the number of arrangements for which M equals 5. Find the remainder when it's a bit of 1000. So I just put like M5 there because just for now, we'll find out the permutations like when you order them later. But what's most important is that this one, there's like 4 and 4, because if 5 is the median of its like row 2, then there has to be one number greater than it and one number smaller than it. And so that is like, if you looked at the numbers, there's like 4 numbers greater than it and 4 numbers smaller than it. So that's 4 times 4 for the row 5 is in. What is next? Okay, and then I just said there were 3 rows that 5 could go in, so that's like times 3 factorial, because you can order these rows. And then I just said I don't really care about the rest. I'm sure it'll all work out. So I just said times 6 factorial. If you just order this rest of the 6 numbers, and I just said that this was my answer, which comes up to, oh, I didn't calculate it wholly out, but it's just 360 as when it's divided by 1000.
Okay. Thank you for your explanation. And I believe the answer is 360. Okay, so does anybody have any questions for this question?
I'm just wondering why, is this okay? I mean, I just said 6 factorial. I didn't really think about if it was like,
Yeah, that's okay.
okay.
Oh yeah, I have a question. So like, you said that the numbers around the 5 can be 4. There's like 4 times 4 possibilities, right?
Yeah.
You got the answer of 360, but I was wondering like, where did you account for the fact that like, on the left side it could be the smaller numbers, and on the left side it could also be the larger numbers?
Oh, that's like the 3 factorial. So the
Oh.
3 factorial is like the one that orders row 2.
Oh, okay.
Yeah.
Okay, yeah, that makes sense.
Yeah. And then the 3 would be whether 5 would go in 1, 2, or 3. And then 4 times 4, and then 6 factorials for the rest of the numbers.
Yeah. Yeah, though, like this is almost what I did, except I did the 4 times 4 times 2. So then we would like, I guess you could say, lock in the positions for the larger and the smaller number, and then multiply by 6 factorial to get like the rest of the numbers and get them all locked in. And then I would find out the permutations for where the 5 would go, which is like the process is almost the same, but it's just slight differences.
Okay. Nice.
Yeah. Okay. Okay, so does anybody else have another solution or any questions to this solution? No? Okay. All right. Okay, then I guess we'll move on to the next question. So yeah, the next person to do number 3. Number 3, Harry, if you would like to explain number 3.
Should I go again?
You could. You don't have to.
I mean, I'll go if no one else wants. Actually, yeah, I'll
All
just
right.
do this.
Yeah.
Okay, so like call the set S product free if there does not exist A, B, C, and S not necessarily distinct such that A, B equals C. And then our set is going to be 1 through 10. I'm not gonna write it out. My handwriting is not very good. Just like from the basic definition, you can't have 1 in the subset because 1 times 1 is 1, so that's already invalidation. So, and then I'm just gonna go like from 1, 2, 3, because those are the only ones that have like squares inside them. So like 2 squared would be 4, so that's a problem. 3 squared would be 9, that's a problem. And then once you get to 4, 4 times anything in the set, if 4 is the smallest element in like the subset, then there's gonna be no problems because there won't be a C with such that like 4 times anything is gonna be within the set if 4 is the smallest number. So I'm just focusing on these 2 and 3 as the smallest. And then 4, 5, 6, 7, 8, 9, we can just do 2 to the whatever. But if we look at 2 first, I'm gonna clear some stuff too. We have to think, okay, so 2 times 3 is 6, so that's gonna be a problem. And we still have 3 times 3 is 9, so this set will be a problem, or these set of numbers will be a problem with each other. 5 and 10 will be a problem with each other. And 4 cannot exist in the set. So, okay. So if 4 cannot exist in the set, that means 8 is a-okay to go, and so is 7. So this is like 2 squared extra. You can just tack on to the end when you multiply it all out. All right, so for this, we can just count how many subsets work. So there's the empty subset. There's each one individually. I can't do this well. 3 can't pair up with anything, so the only other one is 6 and 9. So this gives us 5, I believe. Sure, I think so. I can't remember. Anyways, 5 and 10, you can only have one or the other, or none of them, so that gives you 3. So this gives us 60. Yes, so now we have 60 possibilities for 2. So then we look at 3. The only problems with 3 is going to be 3 and 9, right? Because 3 times 3 is 9, 3 times 4 is 12, we don't have to worry about that. So we just raise a 9, 4, 5, 6, 7, 8, 10. So this is 2 to the 6th. So this is going to be 64. And then for the rest, we can just say for of these rest of the smallest numbers, we have 2 to the 7th possibility, so that's 128. And then when you add this all up, it's 252. And that's it.
Okay, so I don't think I could add anything onto that. That's, I guess, a very good solution and explanation. So does anybody have any questions or comments?
I have a question, is that how can you be sure that you haven't overcounted? Because I frequently make mistakes on that. So
Well, yeah. So here the absolute fact is that we have to have a 2 as the smallest element. Yeah. So this is
when
like
you're
based on like,
designing the case.
yeah.
Oh, okay, that's smart.
Any other questions? If not, then let's move on to question number 4. Okay, so Ian, if you would like to present question number 4.
Okay. Can you see this?
Yeah.
So we can find an explicit formula for a to the n. So we know that the average was like 8. Why is this being weird? A1 plus A2 plus A3 plus all the way to an. This is equal to the number of terms, which is n times the average, which is 2 to the n. If we minus all the terms besides a the n term, then we have n minus 1 times 2 to the n minus 1. So that means the n term is n times 2 to the n minus 1 times 2 to the n minus 1. So if we work this out for 4, 5, 6, 7, 8, and 9, then we have 4 times 2 to the 4 minus 3 times 2 to the 3 plus 5 times 2 to the 5 minus 4 times 2 to the 4 until we have 9 times 2 to the 9 minus 8 times 2 to the 8. So all of these terms here cancel. And then we have 9 times 2 to the 9 times 2 to the 9 minus 3 times 2 to the 3. But in order to get the average, we need to divide by the total number of terms, which is 6. And then my final result was 764.
Okay, thank you for presenting, and I believe that is the right answer. And so does anybody have any questions or like, I guess a faster solution to this problem? I mean, this solution is pretty fast, but like,
I mean, oh,
do you want to say it?
did you do like the sum of A9 minus the sum of A3 and then
Yeah.
the average of that? Yeah. Okay.
yeah, that was what I was thinking as well, and that's also what I did. So just like you guys said, the average of like A1 all the way to A9 times 9 minus 3 times the average from A1 to A3, and then divide by 6. So yeah, I mean this method works as well, and it probably doesn't make the biggest difference, but I guess that's a slight distinction in our problem solving methods.
Should I stop sharing?
Sure. Okay, and then question number 5. So does anybody know the solution to question number 5? Okay, then I guess I'll explain this question. So I need to put my computer down so I can see my monitor. Okay. Hopefully you can see this. Okay, so question number 5. A calculator has a display which shows a non-negative integer n and a button which replaces n by a positive integer chosen random uniformly from the set 0, 1 all the way to n minus 1, provided that n is larger than 0. Initially, the display holds the number n is equal to 2010. If the button is pressed repeatedly until n equals 0, the probability that the numbers 1, 10, 100, and 1,000 will show up at some point can be expressed as m over n for relatively prime positive integers mn. Find the remainder when m plus n is divided by 1,000. Okay, so for this problem, you have to find the probability of a lot of things, and it may feel like it's going to be really hard tracking the probability of starting from n equals 2010 all the way to getting down to 1,000. Like, how are we supposed to find the probability? Well, let's do a few, like for these questions, sometimes it's easier if you start with a smaller sample. So like, for example, if you have big N is equal to 3 and you're trying to reach 1, or you're trying to reach 2, and you can often find patterns that way. But I'll do a generalized like solution for finding the probability of these terms. Okay, so first off, let's say we have we're trying to find the probability of n, and actually, yeah, okay, let's do this. So the probability of AB, which means that so A is so n is equal to A, and we are trying to find the probability of reaching B. Okay, so let's try a few numbers at first. So first off, we have the probability of starting from n plus 1 and getting n. So if we start from n plus 1 and we're trying to get to n, we see that we can go from n plus 1 to 0, 1, all the way to n, which means that the probability of getting n is a 1 in n plus 1 chance, because there's n plus 1 numbers to choose from, and since they're all uniformly random, then that means we have a 1 over n plus 1 chance of getting n, and we can't get n from any other number. For example, if we go from n plus 1 to n minus 1, then n minus 1 would be smaller than n, so you can't go from n minus 1 to n based on our rules. Which means the only way to get from n plus 1 to n is to like directly and randomly get the 1 over n plus 1 chance. Okay, so now let's look at the probability of n plus 2 to n. So if we have n plus 2 to n, the first like a possibility is that we go from n plus 2 straight to n. So we have a 1 in n plus 2 chance. And then we can add the probability of getting to n by n plus 2 to n plus 1 to n. So the chances of getting from n plus 2 to n plus 1 is going to be 1 over n plus 2, and then we multiply by the chances from getting n plus 1 to n, which is 1 over n plus 1. And then if we add these together, then we get 1 over n plus 2 times 1 plus 1 over n plus 1, and then this is equal to 1 over n plus 2 times, this is, the top part is going to be n plus 2 over n plus 1. And then if we multiply this, we get this, the chances of getting from n plus 2 to n is going to be 1 over n plus 1. So it's the same probability as getting from n plus 1 to n. And now let's test a few more values. If we're trying to get from n plus 3 to n, then we can get from n plus 3, first off, we can get from n plus 3 directly to n. So it's a 1 over n plus 3 plus, and then we have the chance of getting from n plus 3 to n plus 2 and then to n. So it's another 1 over n plus 3 times the chances of getting from n plus 2 to n, which is 1 over n plus 1. And then we add the fact that we can get from n plus 3 directly to n plus 1 and then to n. So if we go from n plus 3, we have to n plus 1, we have a 1 over n plus 3 chance of getting there. And then we have a 1 over n plus 1 chance of getting to n. And if we add them together, we get that we have 1 over n plus 3 times n plus 3 over n plus 1. N plus 1. Okay, so we see that the probability of this is going to be equal to 1 over n plus 1. And we're kind of seeing a pattern here, right? Like the chances of getting from n plus 1 to n is equal to 1 over n plus 1. The chances of getting from n plus 2 to n is also 1 over n plus 1. And the chances of getting from n plus 3 to n is also n plus 1. So can we make a general argument for the like, can we prove that this is true for all integers? So like, if, for example, if we start from an integer n plus k, the chances of getting to n is always going to be 1 over n plus 1. So let's try that. So we have the probability of n plus k to n. Okay, so our first probability obviously is going to be the chance that we get straight from n plus k to n. So we have a 1 in n plus k chance. And then we add another 1 over n plus k chance for the chance to get to n plus k minus 1 and then to n. And so now we're going to do something called proving by induction. So induction is basically where you have like a beginning, kind of like a beginning, you know that the beginning is true, and you can use your previous values to try and prove the next values. And then you can use those previous values to keep like calculating the next values, which means that it'll basically be a proof. Okay, so if we're going to be proving by induction, then let's assume, right? So before we all do this, let's assume that all p n plus k minus 1, actually, should I use p? I think I should use m. That all with m it being less than or equal to k is equal to 1 over n plus 1. So here's our assumption. And then based on our assumption, we see that the probability of n plus k to n is 1 over n plus k plus 1 over n plus k times 1 over n plus 1 plus 1 over n plus k times 1 over n plus 1, and then so on. And this will repeat for, because we're starting from n plus k, and we're going down to n plus 1. So the n plus k term, like it's not counted, so we start from n plus k minus 1. Actually, okay, yeah, so this, and then dot dot dot, and this is equal to, we see that there's a common term of 1 over n plus k, so we can take it out, 1 over n plus k, and then we multiply it by, okay, so we need to multiply it by the 1 over n plus 1. Wait, let me just write it out. So like, new space, n plus k, and then times 1 over, actually plus 1 over n plus k times 1 over n plus 1. And then we have to multiply the total amount of terms, that is 1 over n plus k times 1 over n plus 1, which, because we can go from n plus k to n plus k minus 1 to n. We can go from n plus k to n plus k minus 2 to n, and so on until we go from n plus k to n plus 1 all the way to n. So then there will be terms going from n plus 1 all the way to it will go from n plus 1 all the way to n plus k minus 1, which will be k minus 1 numbers. K minus 1 numbers. Okay, and now if we combine this. Okay, so we have 1 over n plus k multiplied by, we have the 1 plus the n plus 1 k minus 1 over n plus k. And then, so then if we simplify this, we get 1 over n plus k times, and so the 1 turns into n plus k over n plus k. So we have, oh wait 1 second. This is correct. Wait, I need to check if this is correct. Okay. Oh wait, no, this is n plus, this is n plus, this is n plus 1. Okay, yeah, that explains a lot of things. And then up here we have n plus 1 plus k minus 1. So then we have n plus k up here divided by n plus 1. So then we have 1 over n plus k times n plus k divided by n minus 1. And this in the end is equal to 1 over n plus 1. So there we have it. We proved that the probability of going from n plus k to n is equal to 1 over n plus 1. And we see that we did an assumption earlier. Let's assume that for all p n plus m minus 1 all the way to n, m is smaller or equal to k and is equal to 1 over n plus 1. So if we start from the base case, n plus 1, we can see this is evidently true. And then if we go up to n plus 2, well, the terms before the n plus 2 will be the n plus 1 term, which is the base term, and it is equal to 1 over n plus 1. So that fulfills the assumptions, which means that the probability of this is also going to be equal to 1 over n plus 1. And then we have the probability of n plus 3 leading to n. And since all our previous assumptions were true, then that means it also leads to 1 over n plus 1. And this will go on infinitely. Okay, so now we've finally proved the fact that for all p, a, b, with n equal a, and we're trying to find the probability of reaching b, the probability will be 1 over b plus 1. Okay, so what does that mean? That means that if we're going to go from 2010 all the way to 1,000, right, then the probability of 2010, 1,000 is going to be equal to 1 over 1,001. And then we can multiply this by the probability of starting from 2010, or actually 1,000 as well, and getting 100. So let's just say actually 1,000 to 100, because we need to get to 1,000 first, but it doesn't really matter anyways. This is equal to 1 over 101. And then we multiply the probability of what was it? 10. Yeah, okay. Of 100 to 10, and this is equal to 1 over 11. And the probability of 10 to 1 is equal to 1 over 2. And if we multiply all these numbers together, oh wait, I forgot to find the product. Wait, let me just calculate this quickly. Okay, yeah. Okay, so then the probability is 1 over 2224,222. And then that means, and since 1 and 2224,222 is relatively prime, then the remainder when m plus n is divided by 1,000, aka 1 plus this number, divided by 1,000, which is what the question is asking, is going to be equal to 223. So the answer to the problem will be 223. Okay, so that was a bit of a mouthful. So does anybody have any questions? And let me just check a chat. Okay. And does anybody, yeah, okay, so no questions? Any comments?
Harry, do you have another solution?
No, I thought it said one, I thought it meant 1, 10, 100, or 1,000, so I was just really confused. And I was just like, I'm not doing this.
Oh, okay,
Yeah.
understandable. Yeah, I guess the wording is kind of weird.
Yeah.
All right, then I guess we'll move on to the next question. So question number 6. Question number 6, Benjamin, if you would like to explain question number 6.
First of all, the problem is that by positive divisor of a natural number, we mean a positive integral divisor other than 1 and the number itself. A natural number greater than 1 will be called nice if it is equal to the product of its distinct proper divisors. What is the sum of the first 10 nice numbers? So we're saying for every factor, and there's another factor which multiplies to n. Factor f, and for perfect squares, then this for the fact that is the square root of the perfect square, then then the opposite factor is itself. So that means that n1 and n are one of the pairings of the factors of n. And the product of all the factors of n is equal to n. Is equal to n to the number of factors over 2. Because each because like I said, for every factor there's another factor that multiplies to n, so and the pairings are unique, so that means there won't be like no factor will have two opposites. But since 1 and n are not proper divisors of n, that means 1 and n cannot be counted in the total, which would mean that n, the total product for all the proper divisors is equal to n to the number of factors minus 2 over 2. And for this to be equal to n, as the problem states, then the number of factors must be 4. There are two types of numbers which have the number of factors equal to 4, p cubed and p to the first times q to the first, assuming that p and q are primes. And then, well, I just found all the smallest of them, which happen to be 6, 10, 15, 14, 15, 21, 26, 33, 34, and 8 and 27, and just add them all up for a total of 182. So I think that's it.
Okay, yeah, that's great. I think you do have like a minor error. The 22 also counts in the
Oh
like
yeah,
prime times prime.
I forgot about
Yeah,
that.
no problem. Well, I mean, like, I guess the reasoning and the explanation of the problem was pretty good. So yeah, and so does anybody have any questions or comments on this question?
I think I'm not sure what the first 4 lines exactly mean.
Oh, well, there's n has like a certain number, every number n has a certain number of factors. And then you can split the factors into pairs of 2 because each pair will multiply to n. But the pair 1 and n are exempted because they're not proper divisors. And so for all factors, then the product of all of the factors of n would be n to the number of factors over 2, because you can pair up the factors so that like in each pair it multiplies to n. And then but excluding 1 and n, it would just be n to the number of factors minus 2 over 2.
Okay.
Product of all the proper divisors.
So
So basically,
what if the factors are the same? Like if n is a perfect square?
then it would be its own. Then it'd be its own pair and would also, but wouldn't affect this because you would just be adding the square root of n on it. But for here, you'd be adding the square root of n on, or n to the 1, or multiplying on n to the 1/2. And
Yeah,
but
so
the thing would only add 1 factor to the total, so it wouldn't matter.
yeah, so basically if we like used an example, let's say 36, right? Because 36 is kind of a small number and it has like powers of 2 and powers of 3, and it is a perfect square, so we can use that. So first off, like let's say you're looking for the factors of 36. Like what would you do? Well, yeah, you would think of like, for example, well, 1 is a factor of 36, right? Which means that 36 is also a factor. And 2 is a factor of 36 as well, which means that 36 divided by 2 is 18 is also a factor. And then 3 is also a factor of 36, so 12 would also be another factor. And then 4 would also be a factor, and 9 would be another factor. And 6 would be a factor, but 6 times 6 is 36 itself. So we can see that we have like these factor pairs that multiply up to 36. So we have 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. And we do the number of factors divided by 2, which means that since like, for example, we take the pair 2 and 18, right? So if we multiply 2 and 18, it's equal to 36. But that used 2 factors of 36. Which means that for each individual factor, it's like kind of like you take the average of the product, right? You take the average of the product, and all of the terms basically turn into 6, which is the n divided by 2. And we have the number of factors because we can basically just average all of them out, and we will have the amount of we will basically average them out into n to the power of 1/2, which is n square rooted. And then we will have like in the case of 36, we will have 9 factors. So then we have 6 to the power of 9. So I guess that's a way of looking at like n to the power of the number of factors divided by 2. Okay, so are there any more questions? All right. So, and before we move on to the next question, does anybody know how to calculate the amount of the number of factors of any number?
Is it like you do if you have any cos p to the e p1 to the e1 times p2 to the e2 all the way to pk to the ek, it's e1 plus 1 times e2 plus 2 plus e3 plus 3 all the way to e1 plus 1, e2 plus 1, e3 plus 1 all the way to ek plus 1. And you multiply them all.
Yeah, exactly. All right. So if we don't have any more comments or questions, then we'll move on to our next question. Number 7. So are there any volunteers to do number 7?
I can do number 7.
All right, sure.
Okay. Oops. Okay, so the problem asks, you have a sum of cubes, and you're given that this is equal to k times k plus 1 times 2k plus 1 over 6. And it asks you to find the smallest, well, this should be a k. It asks you to find the smallest k such that this quantity is divisible by 200. 0 mod, why did I do that? Where's my controls? Okay, 0 mod 200. So I started with saying that if this was divisible by 200, then the numerator had to be divisible by 1200. And 1200 factors to 2 to the 4 times 3 times 5 squared, I think. This is 16, you have a 3, and you have a 25. So first, let's take care of the 3. So I'm going to prove that this is always divisible by 3, just using testing it out. So if k is 0 mod 3, then it's already divisible by 3. If k is 2 mod 3, then k plus 1 is going to be 0 mod 3, and the thing is divisible by 3 again. We're only considering the numerator. I forgot to say that. And finally, if k is 1, k plus 1 is 2, and 2k plus 1 is going to be 0 mod 3. So you'll always have a factor of 3 in the numerator. So we don't have to worry about that. So we just have this and this. Okay. So first of all, this one is always going to be odd. So either k or k plus 1 has to be divisible by 16. And I think I tested small values of small multiples of 16. But another thing is one of these has to be a multiple of 25. So I think...
Wait, 1 second. Before you continue, would you like to prove that like only one of the values have to be like does one of the values have to be 16? What if it's like a 2 and an 8 or a 4 times a 4?
Okay, yeah. So 16 is a perfect power of 2. So if it's not divisible by 2, then it's not divisible by 16 either. If k is even, then k plus 1 is odd, and 2k plus 1 is also odd. So if k is the one divisible by 16, none of the other ones are. If k is divisible by 2, none of the other ones are. If k plus 1 is divisible by 2, then k has to be odd, and this one also has to be odd. So we know that one of the factors has to have all of the 16s. I think if you test it out, it also shows that only one of these can be a multiple of 5. I'm not sure about that though. So let's take the 16, and Wait, I used the fact that 25 has to be in one of them.
Well, okay. Well, I mean, your assumptions are correct. So 25 can only be in one of them because let's say k was divisible by 5, right? So k would be 0 mod 5 and k plus 1 would be 1 mod 5. And then 2k plus 1 would be also 1 mod 5. And then if k plus 1 was divisible by 5, which means that k would be 4 mod 5, then we know that k obviously can't be divisible by 5. And 2k plus 1 is going to be 2k plus 1 is going to be also 4 mod. Yeah, no, yeah, 2 wait a minute. No. 4 plus 1 and then 8 plus 1, so that would be 9. Yeah, 2k plus 1 would also be 4 mod 5. And then if 2k plus 1 was 0 mod 5, it would mean that k would be 2 mod 5. But if k was 2 mod 5, then neither k or k plus 1 would be divisible by 5. So only one of them can ever be divisible by 5 at a time, which means that one of them has to be divisible by 25.
Yeah. So I think I did this right. And there are no 2 zeros in a single row, which means that no 2 factors are simultaneously divisible by 5. And so I just tested out multiples of 5, multiples of 25. So if the multiple of 16 and the multiple of 25 were together, then the smallest value would be 16 times 25 minus 1. If k plus 1 was 16 times 25, then k would be 1 less than that, and that would be 400. So 400 minus 1. So 399 would work, but let's see if we can go smaller than that. So what if the 16 and the 25 were separate from each other? So since all of the multiples of 2 were in the 16, then the 25 has to be odd. So you can test like 25, 75, 125, 175, and so on and so forth. So since this one's odd, k or 2k has to be 1 less than that. So 24, 74, 124, 174, etc. And then eventually I found that 224 was divisible by 25. I mean, was divisible by 32. So we can make it smaller by setting 2k equal to 224, which meant that k was equal to 112. And this is 112, this one would be 113, and this one would be 224. And I think that works. No,
And that,
I wrote it
yeah,
wrong.
225.
This approach was probably very roundabout, so I think there are shortcuts and other time saves.
Yeah, so like in the end, you still have to like, I guess, list all the values out to find the least value. But I mean, I guess like your way wasn't bad, but like I guess there are slightly, actually, yeah, your way wasn't that bad, but like what I did was that I listed out all the values, all the relatively small values for like k plus 1 and 2k plus 1, so that would be divisible by 25. So like I would list out all the values of all the small values of like k is equivalent to 0 mod 25, and k is equivalent to 24 mod 25 for the k+1 term, and k is equivalent to 12 mod 25 for the 2k+1 term. And then I just plugged in all the values into the equation to see if it was divisible by 16. And so I guess this way you wouldn't really like miss any values if you, I guess, just wrote them all down as a list and tested them one by one. Yeah. But otherwise, that's, yeah, pretty good. And also I wanted to add a note onto like the divisible by 3 part. Like it's not anything really too important, but like another way of saying that the k plus k times k+1 times 2k+1 is that obviously it's equal to the sum of these squares. So all of these squares are going to be positive integers. So if you sum together a bunch of positive integers, they're going to be equal to a positive integer. So then that means we have the 6 here, right? It means that k times k+1 times 2k+1 is always going to be divisible by 6. So like it's not that important, but like still. And so does anybody else have any comments or questions? No? Okay. And does anybody else know, does anybody know how to prove that the 1 square plus 2 square plus 3 square all the way to k squared is actually equal to k times k+1 times 2k+1 divided by 6?
Is it induction still?
Yeah.
Yeah. Yeah, it's induction. Oh yeah, also it's 1 squared.
Wait, it's squared?
It's squared, yeah.
Oh, I must have.
Yeah.
I copied it down wrong. Okay.
Yeah, so by induction, it's pretty easy to prove. But does anybody know like how this was discovered? Because proving this theorem is one thing, but like discovering this theorem is another.
Oh, it was like a geometric thing, right? And then
I'm not too sure myself either.
And then I think you rearranged it somehow, like you took this length and then maybe, oh wait, I think I know what it is. So you, instead of forming it into the sum of squares, you divide it into long rectangles, and then I think you add them up that way or something, and then it gives you a different result.
Oh,
Like it's just, you change how you find the area. Instead of representing the area as the sum of each individual square, you rearrange it somehow, and then it combines into a nice formula.
yeah, wait, so let me try this out. So I think like the first row, because the width of, is it the width? Yeah, it's the width of the rectangle is like 1 each. So then we would have like 1 times 1 plus 2 plus 3 plus all the way to k. So that would be 1 plus k times k divided by 2. And we would add like 1 plus k minus 1 times k minus 1. Wait, no, that's not right. No, it would be 2 added all the way to k, whatever. Yeah. So some probably, yeah, I think you're right. It's probably something to do with like the squares stacking. Okay. So does anybody else have any other questions or comments? No? Okay. Okay, so I guess that's all for today's meeting / discussion.
So do you anyone have any suggestion or ideas about our meeting?
And can anyone guess what was the theme of today's meeting? Like what area of math?
discrete? That's a bit
Um,
general.
Number
I think
theory,
it's number theory.
yeah.
Yeah, number theory. That was the main thing we did it on.